Hello, welcome back. In the last lecture, we learned about scatter plot and bar plot. This lecture will be a continuation of that bar plot to create a box plot and histograms. I will start first with histogram. With an example, I will explain why do you need a histogram in place of bar plot, and then I will move into box plot. Suppose I have a data from a examination. I have 40 students, their roll numbers are 1 to 40 and they have got different marks from out of 50. For example, the first guy has got 45 and the second student has got 30 and so on. Now, how can I represent this data? We have learned bar plot earlier. So, I can consider each of these student is a category because he or she is an individual, and then I can plot those students in the horizontal axis and their marks in the vertical axis and show them by a bar plot. That will look something like this. I have just roughly drawn by hand. Now, looking at this diagram where I have marks in the vertical axis and the roll numbers or the categories or the classes of the students in the horizontal axis, this graph represents the data, but it actually does not give any story out of it, right. It does not tell me any story. What I know here is the first one has got around 45, second one has got around 30, something like that. That's the information I get only. Now, if you are looking at this data, you may be interested to know, I am not bothered about how individual student has got. That individual student will be interested to know about, but rather from an outsider as a teacher or somebody who is looking at the data, you may be interested to know the distribution pattern of the data. By distribution pattern, I mean, how many people have got above 40, how many people have got below 10, something like that, right. And that is where histogram or frequency histogram comes into work. So, what I have to do to create a histogram? I have to take the raw data and then I have to bin the data. What do I mean by bin? Bins mean you create some buckets. For example, I take the first bucket as the range from 0 to 10. So, anybody who has got a marks between 0 to 10 belongs to this first bucket or first bin. And then so on, I can keep on going 11 to 20, one bucket, another bucket, third bucket is 21 to 30, something like that, up to 40 to 50 my last bucket. So, these are my bins. I have created 5 bins, and then I look into my raw data and I count how many students are in the bin for the first one, where what do I mean by that? I count how many student has got marks from 0 to 10. So, the result says here in the raw data, if I look into, I see that maybe 4 student has got marks from 0 to 10. So, I put that corresponding to 0 to 10 bin. Similarly, there may be 10 student who has got marks between 30 to 40. So, the count for the bin 30 to 40 is 10. Now, I have these two variable marks range or bins and the count of the student in each of these bin. Now, I will create a bar plot for these pairwise data. What I will do? I will take the middle point of each bin, right, midpoint of each bin. For example, 0 to 10, the midpoint will be 5. So, for 5, I will put a bar of height 4, and that is what I have done in this histogram. Then 15 is the midpoint for the second bin, marks 11 to 20, and I have created a bar there of height equal to 8. In this way, I have created all the bars. And this is my histogram where I have the marks in the horizontal axis and the count number of students in each category, each bin is on the vertical axis. Looking at this, you can easily see there is quite a good distribution of marks. There is not much skew in it. Most of the people have got marks in the third bin, which is 21 to 30. So, that is what you expect in on an average class, and there are some people who are a bit outlier who have got very high marks. So, they are in the fifth bin, and there are some students who have performed a bit low. So, they are in the lowest bin. Now, looking at this histogram as a whole, I have got the comprehensive information about the distribution. So, this is histogram, sometime we may call it frequency histogram, right. And here I have plotted the count, raw count in the vertical axis. You can convert it into fraction also. For example, I have 40 students. So, in the first bin 0 to 10, I have 4 students. So, 4 divided by 40 is 1 by 10. So, you can plot the fraction values here on the vertical axis. So, the height of this first bar will be 0.1. You can convert this into percentage also, if you want to say okay, I want to know the percentage of students in different groups, right. So, in that case 0.1 is 10%, you can calculate the percentage from the original count data also. So, this is histogram. So, now I will move to R Studio and I will analyze the data coming from flow cytometry, and I will try to plot a histogram using R. So, I have a data set coming from flow cytometry. What I have done, I have extracted it as a CSV file. So, let me first read that file, load it to my space, and then I will discuss what is there in this data. So, I am reading this flow.csv file and storing the data in F. Let me open F. So, if you can see here, we have 20,000 observation, right, written for 8 variable. So, this 20,000 is actually 20,000 individual cells. If you remember, in flow cytometry you assay individual cell one at a time, right. So, we have passed 20,000 cells. So, 20,000 observations are there, and for each cell we have measured 8 variable. What are those? FSCH, H stands for height. I will not go in detail of what does that mean, you must be knowing flow cytometry. So, forward scatter, SSC, side scatter, FL1, FL2, FL3, these are the fluorescence channels. So, for each of these cell I have these data. For example, if I look into the FL2H, 310 is the value of fluorescence in the second channel, FL2 channel, for the cell 1, and the unit is arbitrary, right. Similarly, 98 is the value of the fluorescent intensity for FL2 channel for the second cell, something like this. So, in this way I have 20,000 cells. Now, if you just create a bar plot for this, it will be meaningless, right. Rather, in this case, as you have seen in any flow cytometry data presentation, what we do, we try to create a histogram, distribution of fluorescence intensity, right. So, that is what I will do. I will try to plot a histogram for all cell for this FL2H, right. So, for this column FL2H, I will try to plot a histogram. So, let me see. To do the create the histogram, R has an inbuilt function called hist. I will use that. So, I will use F $sign FL2H, FL2H is the variable of the F object, right. So, I want that column data and I want to create a histogram. So, I am using just one argument for hist function, and that will create me a plot. So, let us first create that and then I will proceed. So, this is my histogram. I will not zoom into it, but you can easily see what we have. It has frequency written on the vertical axis. In essence, in R, by frequency they mean count. Okay, and in the vertical axis you have the readings for FL2H, and it has lots of multiple binning has been done, and for each bin it has plotted the bar, right. So, this is what the distribution, frequency distribution of FL2H reading in my 20,000 cell in this particular experiment. Now, what obviously I will prefer to do, I will want to do some formatting of this plot, so that it looks more aesthetically better and gives more information. So, let me first do the formatting and create a new plot, and then I will explain what I am doing, what are the argument I am using here. Okay. So, let me zoom. Now, it looks more professional. So, what I have done, I have written FL2H the way you write in the horizontal axis, and on the vertical axis I have count written. So, if you see, I have said x label equal to FL2H, and I have given the second argument to hist, that y lab equal to count. So, that is how it has written these two text, and I have done some rearrangement or rescaling of the vertical horizontal axis to accommodate all the data, all the bars within the plot nicely. So, what I have done, I have set the horizontal axis x limit equal to 0 to 1000, whereas for the vertical axis I have chosen y limit equal to c 0 to 4000. So, I am scaling from 0 to 4000, and it looks much better. And another thing, I have removed the title of this graph, which is usually not required. So, main is blank, I have kept here as an argument, and LAS it actually written as 1, because I want now the numbers is 4000, 3000, there is a tick labels for the vertical axis to be horizontal. By default they are vertical, I want to convert them into horizontal the way it is there in this plot. So, I have said LAS equal to 1, and that has given me this nice diagram, nice histogram. Now, one question you must be thinking that, okay, how many bins should be there in my data? In the example of student marks, it is very easy to decide, because I have 50 marks, 0 to 50. Okay, you can say, okay, make a bin of 10 marks each, right, 0 to 10, 11 to 20, something like that. So, it is very easy to decide. But what should I do in this case, right, where I have a large variation in data? If you can see from starting from 0 to even 900 something, it is going, the intensity is going. So, how should I decide what should be the number of bins? Now, one point that we have to remember is that number of bins decide the shape of this histogram. If you reduce the number of bins, the shape will change. If you increase the number of bins, the shape will change. So, what should be the optimum number of bins? There are some thumb rules. Here what we have done, I have used the default option of R, which R has its own function. By default, it will calculate the optimum number of bins and plot it. But now suppose I want to change the bin numbers. I have an idea, or suppose I want to use some other function or other rule to decide what should be the number of bins, optimal number of bins for my histogram. So, that option is also there. So, I will do that now. So, what I will do, I will use there is a rule called Friedman Diaconis rule, and I will use that rule to create a histogram in R. So, I will force our hist function to use that rule. What I am doing, I am just changing one argument here, I am adding one argument at the end. I have written breaks equal to FD, right. So, FD stands for Friedman Diaconis rule. So, I could have placed any value there also. I could have said, okay, makes breaks equal to 50. So, then it will create 50 bins for my data set, right. Here I am leaving it to this rule, FD rule. So, let us create the histogram using this rule. Now, you can easily see the pattern of the diagram, the histogram has slightly changed. It is now much more smoother, and I can see as if there is two hump. One is, this is the main hump near 200, and then maybe I have another subpopulation something here which is coming around 400 to near 400, right. So, as if there is slightly another peak, very low one, which was not visible when I was using the default bin numbers, right. So, there is no hard and fast rule how you will decide the bin. Once you understand the data and you understand the physical meaning of it, and you know what you want to see in that, observe in the data, you can actually decide the optimum number of bins. Now, sometimes in this histogram, this is giving me the distribution, right, but sometimes I want to add some more statistics to this data. For example, I may want to add a marker for the mean of this data or the median of this data. Mean and median will be same if I have a very symmetric data, but it is a skewed data in this case. So, I want to mark this graph for mean of this data and also the median of this data. So, how can I do that? To achieve that, what I will do, I will use the abline function. Abline function adds a straight line, either vertical or horizontal, right. So, I am saying abline in the function's argument, I am saying V, that means vertical, equal to mean of FL to H of this data, right. So, it will calculate the mean and use that to draw a vertical line. I want the thickness or width of the line as 2, and I want the color equal to blue. And the second line is for the median, the same abline function I am using, but I am using the function median to calculate the median of the same data. I am using a different color for that line, I am using it as a red line, and both of them will be vertical. So, V equal to I have written as the first argument. So, if I execute these two lines, now let me zoom, you can now see nicely I have marked the mean and the median, right. So, my mean is blue and the median is red. So, what I have plotted here, if you see, I am plotting by default, R is plotting the frequency, what they call frequency, actually we are plotting the count, right, on the vertical axis. But sometimes you do not want count, you want the frequency to be plotted. The frequency means in the fraction values on the vertical axis, right. R has that option. I will go to the default option and then I will tweak it a bit to create something else. So, what I have to do, if I add another argument, frequency FREQ freq equal to false, then what will happen? R will not plot the count data, rather it will plot the density data. What do I mean by density? If you remember our discussion on probability distribution function, we know I can draw a probability distribution function PDF where the vertical axis is the density, right, and they have the PDF, and the area under the curve of that is the probability, right, and the total area under the curve will be equal to 1. So, the similar thing it will do here. It will calculate the density and put it in the vertical axis and draw the bar plot, right, and the area under this whole curve will be equal to 1. So, let me execute that and see how does it looks like. Okay, here I have. So, what we have here, this vertical axis is actually now the density, right, and that is why it is written density. I could change the axis limits from 0 to, I can increase it so that I can accommodate the whole all the bars inside that. I will not do in that, because if you look into this way of representation, usually in day to day life you do not actually represent data in this way. Yes, you represent fractions or frequency on the vertical axis or sometimes percentage, right, but that is not the density the way we understand PDF. What we want usually, suppose that I will not put the raw count on the vertical axis of my histogram, rather I will put the percentage, right. So, I want to know how many percentage cell are there in a particular bin, right. That is what I said for the marks data also that we explained a few minutes back. So, how can I plot the percentage data in the vertical axis? Let us try that. I have to play a bit with the options that they are for histogram function. What I am doing here in this line is that I am calling hist function and giving the data FL to H, and I am saying plot equal to false, that means I am saying do not plot it, right. But what I am saying, I am doing this, calling this function and assigning the output of that function to a object H. So, now in this line of the script, I will not plot the graph, the histogram, but I will store the data of this histogram into a variable H, and then I will look into this variable H and see its different elements of that. So, let us first do that. So, there is no new plot created, but a H variable is created here. Let me open that. If you look into that, H has multiple things. I would request you to look into two things, this counts and density. So, the counts means it has divided data in different bins, right, and for each bin it has counted how many cells are there. So, for the first bin it has 238 cells, second bin it has 1065 and so on. And the density is the density that it calculated and plotted just now, that we plotted earlier when I said okay, frequency equal to false. So, what I will do, I will change this density data in this H object. I will intentionally tamper it, so that now density will not store this density data, rather it will store the percentage data. How should I do that? Okay. In the next line I am doing it. What I am doing? I am taking the counts data from H. So, H dollar counts, and I am multiplying by 100 because I want to calculate percentage, and then I am dividing it by the sum of all the counts, right. So, for each bin there is a count, you sum them and you put that in the denominator, sum of all the counts, and in the numerator you have individual counts for each bin and you multiply that by 100. So, I get the percentage, and now I assign that data to not a new variable, but to the existing variable H dollar density, mean the density variable, density object in the H variable, right. So, that is how it will get replaced. So, just to remind you, remember these values. I have a density, first value is 0.30238 and it should change, it should become percentage data. So, if I execute it, something has done. So, let me go back to the H data, and now you see the density is something else there, density is changed to 1.19. So, it is no more the density it calculate like frequency distribution density, right. It is now the density in terms of percentage of cell in that bin. Now, I want to plot this H object which has all this information to draw the histogram. So, now what I will do? I will call the plot function. I will not call anymore the hist function because already I have created the histogram, right. I will call the plot function, give the histogram object H as an argument, the first argument. I will set the frequency equal to false because I want to plot the density, not the count, and then I have all these other argument for the graphical thing issues, right, the color, limit of the x and y axis. Let me zoom. Now you can see I have a nice plot where I do not have the raw count in the vertical axis, rather I have percentage of cell. So I can say in this bin near 200, almost maybe 17% of the cells are there. So now it is much more meaningful rather than looking into the count. So this is how you can create histogram. You have to know what you want to understand out of this data, and based upon that you have to choose how will you represent the data in a histogram. Now let me move to the second topic of today's discussion, that is box plot. Many a time we represent data either as scatter plot or bar plot, but plotting data for as a bar plot is not a good idea every time. Let me explain with an example. So here I have suppose a data set, a hypothetical data set from an experiment where we have suppose 30 or 40 animals, and I have 3 groups of animal. In each group I have suppose 40 animals, and I am testing some effect of 1 or 2 drugs. So I have one group which we call untreated, suppose that has 40 animals, and D1 is another group where I have treated with a particular drug or a dose of a drug, and D2 is another group of animals, both having 40 animals each. Now we have treated this animal with the drug, and we have also untreated population, and then we have measured some parameter, suppose some blood parameter, we will not go into that. Now I can represent this data in tabular form in this way. Now to represent it visually, graphically, what we may attempt to do in this case is to create a bar plot. For bar plot, what I will do? I will take the mean of each of this category, right, and then I will plot those mean, the height of those these bars are representing those means, and then I know to calculate the error, right, either the standard error or the standard deviation I will calculate from the data, and I will draw the error bar representing those errors. That is fair enough. That is how we usually many times represent this type of data, and as you can see here, D1 has the higher effect, much higher effect than untreated, whereas D2 has almost similar effect with respect to untreated one. Now this type of plot, when I have a large data set, in each category you have large number of samples, right, is actually a bit confusing. So this type of plot actually many a time, particularly for large data set, when I have large number of sample in each category, are actually not recommended one, because they hides lots of information. Let me explain what do I mean by they hides lots of information. For example, here if I have these 40 animals in this each category, okay, I have calculated the mean and the suppose the standard deviation or standard error, but I know as they are animals, their responses must be quite varying, right. So there must be quite a large variations or heterogeneity in the responses in each category also. The same phenomena will happen if you do some study on human being, or even if you are doing assay on cells where you have taken some large samples from large number of cells, then you will get a heterogeneous population. Now this heterogeneous population, some cell will be near the mean, have the mean behavior, but at the same time many of them may be outliers also. So bar plot hide that heterogeneity information. It only tells me the mean and the standard deviation or the standard error. It does not talk about the outlier or the dispersion of the data as a whole, and that is where box plot comes into work. Let me show how we will represent this same data roughly as a box plot. A box plot will have box, right. So I have 3 boxes for each 3 category, just in place of bars I have the boxes, and I will explain what does a box represent, and then from each box you have something thin hair like thing going out from each box. You can see those are called whiskers, and so a box plot is made up of boxes and whiskers. Apart from that, you can see here, for example, D2 I have 3 circles I have marked, right, those are called outliers. Now I will explain what this box is, what the box is, what a whisker, and what are these outliers. So here I have drawn a box plot, one single box, right. I have drawn it horizontally to accommodate in space, but the formalism will be the same when you will draw vertically also. So a box plot will have a box, and in the middle of the box there will be a line. That line represents the median. How do I get the median of the data? So, suppose I have these 40 untreated animals, right. So, I have measured their blood parameter. So, what I will do, I will arrange this data for this population in a ascending order, suppose lowest to highest, and then I will find the middle point, the middle data, that is the median, and this bar, this vertical bar represent here that median. So, the bar in the middle of the box represent the median of the data. Now, let me go to the edges of this box. On the lower side, on the left hand side of this box, I have marked it by this pink. This is the quartile 1 of the data. How do I get quartile 1? So, take the data less than the median. So, this is the median, take the data below the median and find the middle of that. So, that is your quartile 1. Similarly, the pink line on the other edge, the right hand side edge represent quartile 3, third quartile. What is that? I have the median of the data, you go up on the higher side, take the median of that, the middle point of that. That is my third quartile. So, the box, the lower part, one edge of the box is quartile 1, then the middle line is median or it is quartile 2, and the upper edge, the last line in the box is the quartile 3. And you can easily understand the distance between this quartile 1 and quartile 3 will be called interquartile range or IQR. Now, let me go to the whiskers. From this box we have extended whiskers, right. What does a whisker represent? Here I have written this yellow thing here as the bar where the whisker has ended, I am calling it maximum, whereas on the other side I am calling the end of the whisker as minimum. But please do not get confused that with the minimum and maximum in the data. No, they do not represent minimum or maximum in the data, they represent minimum or maximum in some other sense. What is that? Let me go to the higher side of Q3. So, this whisker represent a range which is representing the data from Q3 plus 1.5 into the interquartile range. So, what is the end of this whisker representing? That end is representing the highest value in my data which is within the range of Q3 quartile 3 plus 1.5 of IQR. So, that is the maximum on that side. What is represented by these on the lower side? So, the whisker in the lower side ends at the value of the data which is the minimum value within the range of Q1 minus 1.5 into IQR. So, this whisker on the higher side is going up to the data point which is within Q3 plus 1.5 into IQR, and this lower whisker going up to the data point which is within the range of Q1 minus 1.5 into IQR. And then what does this red point represent? As I said, they represent, these red circles represent the outliers, right. So, these outliers are outside this range of 1.5 into IQR, the interquartile range on both sides, right, after Q1 and after Q3. Now, why do we choose 1.5 IQR and represent box plot in this way? To understand that, we have to go to standard normal distribution. I will not go into the mathematics of that, but it can be shown that if your data follows standard normal distribution, that means it is a normal distribution with a mean 0 and variance equal to 1, then 50% of the data will remain inside this box, that is within the interquartile range. Whereas, this outlier on both sides, they will constitute only 0.7% of the data. So, 0.7% of the data will represent, for a standard normal distribution, will represent the outliers, and that is why we have designed the box plot in this particular fashion. So, now I will show how to use R to create box plot for a particular data set. So, here I have a script to create box plot. The data that I am using is a default inbuilt data set from R, insect spray. So, what you have here, they have tried different insecticides on insects and then made some counts of insects. So, let me read that data and load that in a variable D. Let us check the data. It is a 2 column data, 2 variables, count and spray. The spray, as you can see, is a category data, right. A, B, C, these are the label E. So, the A up to F, these are different types of spray, A, B, C, D, E up to F. And for each case, you have the count of insects. When they have applied those the sprays on the insect and they have made some count. So, now I want to represent this data not like a bar plot, but as a box plot. So, what I will do? R has a function called box plot and I will use that. In the box plot, obviously, you have to give the data as a argument, that is the second argument, but the first argument is the formula. What does formula represent here? Here I have written count tilde spray. That means I am telling the box plot function that see, my group is based in spray variable. So, there are groups in spray variable A, B, C, D, E. You have to consider that as a group variable and the count is a vector of data where the numerical values are there. So, take the values in the count variable, arrange them as per the group information given in spray variable and give me the box plot. It will do that. So, here I have got the box plot, right. So, you can see each of these category, the spray A to F are there in the horizontal axis and the vertical axis I have the counts and the data is represented as boxes and whiskers along with the outlier. I will do some makeover of that, edit some text and all these things and then I will explain what this box plot is telling us. So, let me first run the modified code for this box plot, then I will explain each of the argument. Okay. Now, I have got the box plot which is looking bit better than the previous one. Let me zoom it and then I will explain each of these argument that I am using. Obviously, the first argument in box plot is now still the formula count tilde spray, then I am declaring the data D, then I am writing X lab, label of X, I am saying this is type of spray and that is in apostrophe, right. That is why type of spray is written here in the horizontal axis. Then I am labeling the y axis, the vertical axis, y lab equal to insect count, again within apostrophe. So, insect count has been used as label of the vertical axis in the plot. I have changed the font size. So, what I am saying that for the both the label and the axis tick, this 0, 10, this is the axis mark, A, B, C are also axis marks and the type of spray and insect count are the labels. So, I want to increase the font size of both of them and I want to make them 1.5 times of the default one. So, I am written cx dot lab equal to 1.5, cx dot axis equal to 1.5. Then I have changed the limit of this vertical axis, I have made it from 0 to 30. So, I have written y limit equal to c 0 30 and I have chosen variable width, var width equal to true, although you do not see much effect of that here. See, many a time what can happen, in each category may not have the same number of samples, right. Maybe in one case you have 40 cases samples, whereas in the other category the sample size is 30 or something like that, and you want to represent that data also in this same box plot. Then what you can write, you can make this variable width, var width equal to true, then this size of these boxes, the width of these boxes will vary. Now, in this case actually all the sample has the same number of samples in that, each category has the same sample size, that is why the variable width does not have much effect to see here. Then what I have done, I have marked this outlier by red color solid fill, right. So, I have set out PCH equal to 19, so it is a filled circle and out color equal to red. So, I am using red color filled circle as outlier. Now, let me look into a bit details in the diagram. So, as I explained, this if you take the F category of spray, right, this thick line inside the box represents the median of the data in that category, right. So, that is quartile 2. The box lower end or lower edge of the box where the box end is my Q1, whereas the upper edge of the box is Q3, quartile 3. And where the whisker ends? Okay, for the lower side of the whisker, lower side whisker, start from Q1, you go down up to the length of 1.5 into IQR. IQR is the length of this box. You go down up to the length of 1.5 IQR and find where you have the minimum data. So, the minimum data is somewhere here. So, the whisker ends there. For the upper whisker, you start from Q3 and keep going up to 1.5 into IQR, right. So, you add 1.5 into IQR above Q3 and you stop at the maximum value in your data, and that is where it has stopped. So, this is the upper whisker ends at the data point which is the maximum value within the range of Q3 plus 1.5 IQR, whereas the lower whisker has ended at the minimum value which is within the range of Q1 minus 1.5 into IQR. Now, let me look into this D and C, right. In this case, you can see the median are either close to Q1 or Q3. That type of data represent actually that the data is very skewed in one side, right. In this case, for example, D, the data is skewed in one direction, whereas for C, the data is skewed in the other direction. And for both C and D, there are two outliers, and those are represented by this red dot, and as I said, they are beyond that limit of 1.5 IQR, right. So, that is all for this video. So, in this lecture we have learned how to create box plot and histogram. See you in the next lecture, and we will learn more about making data visualization using R. Thank you.